Okay. Good morning, everybody. So today, as you can see, there's nothing I'm being quite ambitious. Let's see how far we get. So I want to begin by someone had changed the definition of the Fourier transform. There's a bunch of minus signs. All right, let's see how it goes. Okay, so I'm going to start off by essentially doing a couple of examples. Well, one example that will be quite illustrative about how we think about the inverse of the Fourier transform. And I said that one of the pros of the Fourier transform is that it's easily vertical. The reason it's easily vertical is because the inverse of the Fourier transform is pretty much the Fourier transform. So you say, unlike, for example, the Laplace transform. And then I'm going to take a step back a little bit and recast the idea of what the Fourier transform is in terms of vectors in a function space or Hilbert space. So this will be a slightly abstract way of looking at the problem, but it has the benefit of pretty much all of what we can do thinking about transform methods and framing this way. And then I want to get back to doing one more example, just for illustrative purposes. And this is to look at the Yukawa potential. The Yukawa potential in the context of nuclear physics is quite well known. It's a potential that kind of governs the interactions of subatomic particles with the nucleus. It's an interaction that exponentially decays. We're going to encounter a slightly different form when we try to take the Fourier transform of the Coulomb potential, which is the more familiar inverse square law. What we find is that Coulomb potential, you can't scale up just Fourier transforms. That's because the potential goes at 1 over r squared, and it's divergent. Trying to take the Fourier exponent. So you need to find a way to regulate this potential, and the way you regulate the potential is to put an exponential cutoff. The idea of regulating integrals is one that's going to come up over and over again. So that's why we're going to do it with a simple enough potential. One of the main uses of the Fourier transform methods in general is to solve differential equations. So if we have time today, otherwise we'll do it next week. We're going to solve a very straightforward differential equation. That is the wave equation using the Fourier transform. Again, this is something I expect you probably have seen before. If you have, then great. This is a reminder of how it works. If you haven't, then you can see how exactly it will work. All right, so how did I define the Fourier transform? What's that? Minus I omega t plus. I'll be consistent with that. If it is minus minus. This is one of those things where, depending on the technique you use, there's a plus or minus function. But let's be consistent with what we use last time. So, again, by way of reminder, the statement here is that given a function that is at least square integral f of x, I can define its Fourier transform Stop last time with the direct. The direct. But go further. There's lots of head shaking. I'm not sure what it is.
You stopped at direct.
Okay, I stopped with the direct. Okay. So given the function f of t, say, I multiply this function by e to the minus I omega t, integrate from minus infinity to infinity t, and out pops up to the normalization a new function g of omega, which we call the Fourier transform of f of t. Now, we did an example where I took an exponential e to the mod x or alpha mod x. Yeah, e to the minus alpha mod x, and I did this integral for you. I showed you that very straightforwardly it evaluates to something that goes like alpha over alpha squared plus k squared. Now I would like to do another example. That will illustrate for us how to find the inverse of a Fourier transform, right? So again, we did the example where we mapped the exponential to 1 over, we mapped the exponential e to the minus alpha mod x to 2 alpha over alpha squared plus whatever the parameter was used, k plus that. So now I want to look at a slightly less trivial example. So suppose f of t is now 1 over root 2 pi to alpha over alpha squared plus t squared for alpha subparameter. So again, you should recognize this from the first example. Was the result of the Fourier transform that we carried out. Parameter. So we want to calculate. So we want to ask what is corresponding g of omega, which is 1 over root 2 pi integral e to the minus pi omega t. This f of t dt. And well, if I substitute in here, I'll find that this is 1 over 2 pi. I get another factor of root 2 pi from the function s. Integral minus infinity to infinity. 2 alpha e to the minus pi omega t over alpha squared plus t squared. Which I'm going to choose to the right because I'm doing my integral with respect to t. That's t squared minus alpha squared. This guy gets factorized to t minus alpha times t plus alpha to alpha e to the minus r omega t dt. Sorry. It's a plus. Makes all the difference in the world. Okay. So let's pick some alpha and see what's going on. So the first thing is I'm doing a complex integral. Okay, so it will help to think of t here not as a real variable, but as a complex variable. So let's suppose that instead of doing the integral with respect to t, you'll analytically continue t to some complex number called tau. So on the tau plane, I have two values, plus I alpha, plus I alpha, and the opposite side of the real axis, the value minus I alpha. So these two special points, the special point because they're poles of this integral. Okay. I want to do an integral on the real axis, minus infinity to infinity. This is the real part of this is the imaginary part. So the integral has two simple poles at tau equals plus or minus alpha, and it's easy enough to see that these simple poles have so-called residues. So the residues are e to the plus or minus e to the plus or minus alpha omega over r, depending on whether I'm looking at plus or minus I alpha. So note there that integral as simple poles at plus or minus I alpha with residues plus or minus e to the plus or minus alpha omega over I, respectively. So in order to evaluate the integral, we need to distinguish three different cases depending on side of omega. Case one is if omega is greater than omega is greater than 0, then what I do is I close this contour on the upper half plane. If I close the contour on the upper half plane, I do an integral over, let's call this contour gamma. U for upper half plane. So then the integral is a closed contour integral over gamma u of 2 alpha e to the minus I omega tau over tau squared plus alpha squared tau, which is 2 pi I times the residue of the integrand for f of tau. Residue of f at tau equal to the only pole that's enclosed by this contour, which is the one plus alpha, which is 2 pi I times the plus side of this expression here. So that I is going to cancel out this side. So that's 2 pi times e to the alpha omega. So the first minus sign. Let's see.
Plus I omega. Plus I omega. Plus I on one side. Plus. Omega is greater than 0. Either exponential positive. Half plane. Plus I omega. Plus I omega to there. Minus I times I 1. Plus omega alpha. And
Okay, you know what? I'm gonna change sign of original sign. Sorry. Oops. It will affect you. The rest of you on tablets, which should be fine. Um, Good now, so that for this. So let's see. All right, so I'm going to take my definition to be the forward transform coming with a plus I omega t and the backward transform coming with a minus I omega t. Okay, so let's follow this through and see where it goes. So f of t is this, g of omega is this. So there's the plus sign here, there's the plus sign there. Okay, so let's look at this integrand. It has two poles, plus and minus there, and the residues of the pole are top pole. I will calculate e to the plus I omega t, that becomes plus I minus. Minus plus, and that will be a plus. Denominator, I will have two I alpha. That will cancel off the two alpha there, minus the denominator, and a plus sign from there. The other one will have a minus sign. Okay, so the signs are consistent. That point. Here I have an I omega t tau, d tau. Residue of that is comes with a minus sign there, and comes with a plus sign there. Sorry. Okay, so now on the left-hand side here, this integral has two parts. One part comes from there, from minus infinity to infinity. The other part comes from the curve that, because of the Jordan lemma, I'm not going to get any contribution to the integral. So the left-hand side is simply then the integral that we started off looking at, which is the integral from minus infinity to infinity of 2 alpha e pi t t squared minus plus alpha squared dt. So that tells me then that my g omega is one over 2 pi times 2 pi times e to the minus alpha omega. 2 pi times alpha. G of omega is e to the minus alpha omega. And remember, this goes to omega is less than greater than 0. Similarly, you can show that g of omega and omega is less than 0 is equal to e to the plus alpha omega. Plus alpha omega, because there's a minus sign from here, but there's also a minus sign because you're going around the contour in a clockwise fashion. We generally take counterclockwise to be positive direction. And finally, when omega equals 0, our integral of g of omega is 1 over square root r, integral from minus infinity to infinity of 2 pi of 2 alpha over t squared plus alpha squared dt. This is a simple integral. It's a hyperbolic tan integral. So this evaluates to 1. Sorry, this evaluates to 2 pi. The hyperbolic tan is inverse tan. So it goes from minus pi to pi. So this evaluates to 2 pi, and 2 pi cancels out on 2 pi. So this is so if I put all that together, it follows that the omega is just e to the minus alpha mod omega. So let's take a step back. We started off with this function. We took its Fourier transform. Okay. And we found that it was that function. We took the Fourier transform again, and we found that it's that function. So 2 Fourier transforms give me back the original function and so on. So the Fourier transform, the inverse of the Fourier transform must have the same form as the Fourier transform. The only difference is in the sign of this e to the I over t. So we'll come back to that. Come back to that in a minute. Question? There's a root 2 pi from there, but so my original function that I want to transform comes with a root 2 pi. And the transform itself comes with a root 2 pi. So those two combined to give me this factor of 2 pi. So that's where the 2 pi is. Yeah. Okay. Any questions online? So you can of course play many games with this Fourier transform. So what I'd like to do is to get your hands further dirty, is to show that Fourier transform of a Gaussian is nothing else. Okay. Not the same Gaussian, because remember, one of the properties that we identified of the Fourier transform was that it took a function, and if I squash that original function, that has the effect of stretching out the Fourier transform. Okay, so if I maximally squash it to a Dirac delta, I stretch it out maximally to a constant function. So this is going to map a Gaussian, which is a bell-shaped curve, to another Gaussian, which is another bell-shaped curve. But they're going to have the property that they're going to be related, that as you make this, if you squeeze this Gaussian, it's going to stretch out this Gaussian in the horizontal direction. Right, so the parameters, and you can take the Gaussian to be, you can take this one to be e to the minus a x squared, for example. And this is going to have to depend on a in the inverse fashion. So we'll leave that as an exercise to you. Fun exercise, and you should be careful about which curve you're integrating on the complex plane. Tell you that the easiest curve to integrate on is a rectangle. I didn't give it. So suppose this is point t minus t.
Then we want to integrate one is the one that goes from minus t to t. From minus t plus t, then down to, let's say, t minus I k over a, and then across to minus t minus I k over a, and then up to t. Do the integral in this curve. Okay. So I'm going to write down that the inverse Fourier transform what we've made from the observation that we've made here. So if g of say k is 1 over root 2 pi times the integral from minus infinity to infinity e to the I k x f of x dx, then f of x is 1 over root 2 pi times the integral of e to the minus I k x g of k. So this is the relation between the forward and reverse Fourier transforms, and you can show that if you take f of x, take its Fourier transform, and then take the Fourier transform of the resulting function g of k, you get back f of x. Again, the plus and minus signs here are convention. As long as you're consistent, everything will come up normal. And the 1 over root 2 pi, 1 over root 2 pi here is again convention. Some conventions count this as a 1 over 2 pi, in which case this is a 1, some count inversely, and some go symmetrically between the two. So we're going to make symmetric conventions go between one of the things that you might notice then is that thinking about the Fourier transform this way, and thinking about what we've been saying about integral representations, you can use the Fourier transform to give an integral representation of complicated functions. You know, as an example, we've just done an integral representation for the exponential. We've just learned that this function, e to the minus alpha mod x, can be written as an integral of alpha over pi, integral from minus infinity of e to the minus pi kx over alpha squared plus k squared dk. So this is what I will mean when I say that you can use transforms to generate integral representations of functions. Of course, you know, getting an integral representation for an exponential doesn't really do anything will much good. But more complicated functions, integral representations are incredibly useful. Okay. An example, a real life example, I'm currently working in collaboration with some colleagues and we trying to compute the 4-point function for some particular field, and in it crops up an integral. And it's a very innocuous looking integral. The integral reads minus 30 to 30 sine, which I mean the actual sine of x minus y, sine of y minus z for 2 points, two real numbers x and z, over the absolute value of x minus y, absolute value of y minus z, integrated with y. So this is an integral that crops up in a particular quantum physics problem. Doesn't look particularly difficult. And you recognize that if I give you two numbers, x and y, then the sine of x minus y is the same thing as the absolute value of x minus y divided by x minus y. So I can cancel out these absolute values in the denominator by writing, in which case I'll just have 1 over x minus y, 1 over y minus y. Again, it looks like a fairly innocuous integral that has two poles and y equals to x and y equals to z. The problem is that those poles, because x and y, because x and z are real numbers, those poles lie on the contour of the integration. Right? Unlike these poles, which lie inside the integration. Right? So one way that we found to evaluate this integral was recognizing that this integral actually is an integral representation of a combination of gamma functions. In fact, the combination of the gamma functions are the beta function that we studied already multiplied by something called the hypergeometry. Right? And we happen to know what the values of those functions are for the particular powers of these guys. Right. So you can evaluate this integral just by knowing that there's such an integral representation for a function that you know. That's kind of turning the question around. All right. So these things have real world applications to the extent that the formal field theory is established. Okay. Everything that I've said here, I've said essentially for one-dimensional integrals. So we've only been doing Fourier transforms in one dimension. But you know, it shouldn't be too difficult to convince yourself that they hold a general number of dimensions. There's nothing that I've said which is specific to one dimension. So we can generalize the Fourier transforms to an arbitrary number of dimensions. For example, in 3 dimensions, we'll look like this. So all this generalizes to higher dimensions, e.g. equal 3. I would have some function f of, let's say, r, where r will be the position vector, and I would do an integral over p-dimensional space, so x, y, and z, of f of r e to the I k dot r dv r, and the only thing that will be affected by this is the normalization. Should go like 2 pi power of dimension by 2. Similarly, the inverse f of r in our notation would be 2 pi to 3 halves integral over 3 g of k e to minus I k dot r. Okay. And if you look at this, and if you think back to maybe what you've learned in optics, or even whatever quantum field theory you've learned so far, then one way of thinking about this is an expansion of the function f of r in a continuum of plane waves e to the minus kr. Okay, same thing, you make that with some amplitude, and the amplitude will be g of k. So this is a continuum version of the expansion of f in plane waves e to the minus r with amplitude g. Right, so normally there'd be a discrete sum. All I'm saying is I'm making that discrete sum. Continues. Okay. So now I want to take a step back from this. I want to take a step back from this and just think about these things in a slightly more abstract fashion. The reason I want to do this is because it will give us some intuition for how this was going to work in higher dimensions and more complex, more complicated. All right. So suppose I have some vector in a space of functions. So instead of thinking about a vector space, I'm going to be thinking about a vector in infinite dimensional continuous space, right? Otherwise known as a Hilbert space if I put it in some inner product. So suppose then, and I'm going to be using Dirac notation in this function takes this in this space. Suppose that f is some function in a abstract, it's some abstract vector in a function space. It is a right, so f is a vector in the Hilbert space H. What does any old function space? It's a function space that I'm going to assume has a well-defined notion of an product existing. So the function f of x that we were talking about, I can think of as taking this vector and projecting it onto some position basis. So I can write x then as the projection of the product of this function f onto the basis x. In the same way that you would express it for a discrete
vectors in a finite dimensional vector space. This is a position basis vector. But position basis vectors are not the only vectors that I can use as a basis for this function space. Okay. There's another basis vector that I have that's canonically related to this position basis vector. That's called the momentum basis. And if I take f, the same f, and I project it to the momentum basis, then I get a function of k, I'll call f tilde of k. So this is a momentum basis. Okay. And these two bases, the x and the k bases, are related to each other because if I take the inner product of x with k, then I get the plane wave. Which I'm going to normalize by this factor of 2 pi e2 minus I k x. So what this necessarily means then is that this function f tilde of k, which is this guy, I can insert an identity in here. Those of you who are doing my string theory, string theory, know exactly where I'm going with this. Right? And then I resolve the identity. Why? Because the x basis as well as the k bases are complete. So I can express the identity as a sum or integral over this basis. So this is then k integral x out product x dx. Is the resolution of the identity. And then I partner these two guys and I partner these two guys. This is going to give me f of x. This thing is going to give me this is going to give me f of x, and k in the product x is the complex conjugate of x in the product x in the product k, which just changes this sign here, and it tells me that it tells me that this is just the integral of k in the product x in the product f dx. This here is x in a product k condition conjugate, which is just the integral of one over root the integral of f of x e to the plus I k x. In other words, this f tilde of k, which was the expression of the vector f in the momentum basis, is nothing but the Fourier transform to k space of the function f of x.
But you can see this, you know, in a much more natural way, by just thinking of these guys as the projection of the abstract vector, same abstract vector F in either the position space or momentum space. Okay? And that's all that the Fourier transform does. Is it takes you between the projection of F from position space to momentum space. Okay? That's a really neat way of thinking about, you know, what otherwise seems like a rather ad hoc way of constructing these transforms. Okay. So similarly, I can express, you know, things like the Dirac delta function. Okay. The Dirac delta function in this language Dirac delta, let's say between K and K prime, is nothing but the inner product between the K basis vector and the K prime basis vector. It means, let me show you that this is true. And again, what we do is we insert an identity between these two and we resolve the identity. Resolve the identity in some position basis as well. So this is K integral x x yes K prime which is just 1 over c r times the integral of infinity of e to the I a minus a prime x, which you would recognize as the integral representation for the Dirac delta function. And similarly, if you want to write an expression for delta of x minus x prime, you would exchange the role of x and k, let's say, the exponential here and also. Okay. And again, everything that I've said about one dimension here can be extended to the higher dimensional case. So now, clearly I'm not going to finish what I set out to do for this lecture, but I can at least tackle the power problem. And I'm going to approach the Yukawa problem as a problem of doing Fourier transforms in theta dimensions. Okay. So one of the most important Fourier transforms that you might consider taking if you do basic physics problems is in considering scattering problems. Right? Pretty much everything that we understand about the world around us is a scattering problem. You see each other because light scatters off you and comes from my eyes. Okay. We understand atomic structure because again, we scatter things off atoms and see what comes up. We resolve those things. We see things in the night sky because light scatters off our observational instruments. So, understanding scattering is a problem that extends from atomic physics through to astronomy. One of the very important types of potentials that you would work with in such scattering problem, again because it's a problem that extends from atoms through to the cosmos, is scattering things off a Coulomb potential. Okay. So, in the context of the scattering of stuff of a Coulomb potential V of R, I'm going to be working exclusively in 3 dimensions here. So R is a 3-dimensional position vector, square root of x squared plus y squared plus z squared. And the Coulomb potential is just Q of R. So again, R here is y squared x squared plus y squared plus z squared. So in solving these scattering problems, and again, these are basic problems in magnetism, nuclear forces, even gravity, we'll encounter the following integral. You encounter the following integral. One over 2 pi equals the integral over R3 of e to the I k dot r of q of times q over r d3. Let's call this thing v tilde of k. So essentially, you will need to Fourier transform, for whatever reason, this Coulomb potential. The problem is that this is a divergent integral. So this thing is divergent. As R goes to infinity. Okay. So scientists studying this problem back in the 1950s, so encountered the same divergence. So the question is, how would you do an integral? One way to do this integral that was developed by Hideki Yukawa is to regulate it. Okay. So typically what you would do is you want to regulate this divergence here. So what I would do is have something that acts as an envelope that forces this function into a certain behavior. Okay. What Yukawa did was to replace the Coulomb potential by from V of R to, let's say, V alpha of R. And all the difference between V of R and V alpha of R was instead of having Q of R, you multiply this by an exponentially decaying function of R with some parameter alpha. So Q of R e to the minus alpha R. Right. So the upshot of this is that Yukawa potential, unlike the Coulomb potential, which drops off like 1 over R, is a long range interaction. The Yukawa interaction exponentially falls off in R. So it's a short range interaction. So if you want to try and understand, let's say, the nuclear forces, which are only operational within the nucleus of the atom, then this is a good model because this force exponentially decays as R increases, whereas the Coulomb curve doesn't. In that case, our V of R, or V tilde of K, goes to some V alpha tilde of K, which is just this 1 over 2 pi d halves integral e to the minus e to the plus I K dot R Q e to the minus alpha R. R again is square root of x squared plus y squared plus z squared R. Now you can do this integral. I'm saying is that this integral, unlike the other one, is convergent. Given that everything that we're talking about depends only on the radial distance away from the source of this Coulomb potential, it makes sense to change from Cartesian coordinates x, y, and z, which is implicitly what I'm going to write this down, to polar coordinates. So in polar coordinates, the same integral. Okay, so there's two assumptions of it. One is that I'm going to orient my axes, in particular my z-axis, so that it lines up with K. So orient the z-axis such that K, vector K, is minus K z direction, which means that I'm going to assume polar coordinates, spherical polar coordinates. With this, my integral v tilde of K, alpha, is, take out this charge Q over 2 pi b halves, I should mention this charge. Take out the charge Q, I have an integral from 0 to infinity of the r squared, integral from 0 to pi of the theta sine theta. This comes from the measure of the integral. So this dr becomes sine theta, sorry, r squared sine theta r dr. So it becomes r squared sine theta dr d theta d phi. Okay, so there's a sine theta that comes from the measure, and then I have an integral from 0 to 2 pi. We have the integral angle this is with respect to phi. E to the I, A, R cos e to the minus alpha or okay. Now let me do one more board. There will be 4 more minutes. I'm going to roll the exponential planes this. So notice the following. Firstly, there's no phi dependence in this integral, which means that the phi integral is trivial. We get back to phi over there. This just contributes phi. Secondly, the theta integral looks like this. Integral from 0 pi of sine theta d theta e to the I k r cos theta. If I take variables for theta, cos theta, then d theta sine theta is nothing but minus d of cos theta. Okay. So this just becomes the integral from -1 to 1. -1 to 1 because the minus sign comes from here. Cos of 0 is 1, cos of pi is -1 and so on. Of e to the I a r u du. And this is just e to the I k r minus e to the minus I k r all over I k r. Okay. And I can put this together. Let's take this, substitute it into the R integral. So now I've done everything on this side. I have only the R integral to account for. And I'm going to do this in the next slide too. Show that V alpha tilde of K so the details there is just 2q over the square root of 2 pi times 1 over a squared plus alpha squared. And you can in fact see 2 things. One is the alpha integral, which I needed in here, and the alpha integral, which will be essential, showing that this integral converges, is necessary to make the integral converge. The function is still well defined in the limit that alpha goes to 0. And finally, this expression contains a k squared, which, even though it seems like we made a unjustified assumption by orienting our axes so that k was minus kx, because it only depends on k squared, it actually doesn't matter what orientation your axis has. This k squared will always enter that form. And it's always going to be kx squared, k minus k plus k. Right? So then finally, once you've once you've got this expression for P alpha, we can find the expression for Coulomb interaction, or a transform of Coulomb interaction, by just sending alpha to 0. So just 2q over root 2 pi a squared. Okay, so the story here is one that you will encounter also in your studies, which is that you encounter some divergent quantity, but that divergent quantity actually corresponds to some physical things. In this case, some physical problem involving scattering. Okay, so what we do here is we modify the problem we're trying to study by regulating it. You add some function, you multiply by some function to aggressively cut off this divergence. Right? And then you see what remains finite out. And that thing that remains finite here, once k goes to 0, is the Fourier transform. Okay. This is a very kindergarten way of doing exactly the same thing that you do in quantity theory with the process of renormalization. Right? Essentially, renormalization is pretty much the same thing. You have some divergent quantity, you regulate that quantity, you see what remains finite, you see what you need to add to cancel off that infinite piece. We'll see that again a little later. Thank you.